So here are 6 unit intervals. So when we project them down into the horizontal real axis. And this is the partial order that they define by saying that one is entirely to the right of the other to be greater than it. We can draw notice that they have the elements of this coset have a natural labeling, 1 up to n, by the order of the intervals, from left to right. Draw the strict incidence matrix of this partially ordered set. We put a x here, row I in column j, if I is less than j in the coset. And you can see it's clear from this picture that we're going to sort of trace out the boundary of this diagram. We get a Dyck path. In fact, another characterization of semi-orders is we can order the elements in such a way that this strict incidence matrix is essentially the x's form a diagram of the partition, Young diagram of the partition, reflect in the usual way drawn. No, there's also what I would call unexpected interpretations. It really doesn't seem like it has anything to do with the kind of structures you were looking at before, and the occurrence is very well hidden. For instance, n tuples of integers greater than or equal to 2, such that if you append and prepend a 1 to the sequence, each AI divides the sum of its 2 neighbors. There are the 5 of them for n equals 3. Let me quickly go through why is this counted by Catalan number. Here's an example of such a sequence. One can show pretty easily that if you look at the maximum number, any instance of it occurs more than one, it must be exactly the sum of its 2 neighbors. That's quite easy to see. Moreover, if we remove it, it's also easy to see that we'll get another sequence size 1 smaller. So we'll remove this maximum number, which is 2 plus 3, we'll put a little bar before the 2, the leftmost of the 2 numbers that it's the sum. And then we continue this procedure. So we remove 5, I'll just write it in red to denote that we removed it. Put a bar to the left of 2. Now we can remove 4 and put a bar to the left of 3. Now we have the sequence 1, 2, 3, 1. We remove 3, put another bar to the left of 2. And then 2 to the left of 1. And now we're just trying to left with 2 1s and a bunch of bars. At this whole diagram, replace the 1s by up steps and the integers by down steps, and leave out the last 2 terms, and we'll describe the Dyck path. That's the bisection. Another interesting example that's related to a lot of recent research is cores of partitions lambda. We have a partition lambda, a Young diagram like this. We have a square like this, reddish colored square. We can define this hook to be the set of all squares to the right and below. And the hook length is the size of the hook. So I put these hook lengths here inside each square. They play a very fundamental role in theory of symmetric functions, representation theory of the symmetric group. P-cores, they come up, for instance, in modular representation theory of the symmetric group. They are partitions with no hook length equal to P, or equivalently divisible by P. A PQ-core is a partition that is simultaneously a P-core and Q-core. It's kind of a strange concept, but there's a lot of interesting combinatorics with PQ cores. And it turns out that the partitions that are both n cores and n plus 1 cores is the number of them is the nth Catalan number. Here they are for n equals 3. So I'll try to explain the connection with, let's say, Dyck paths. 5, 6 cores. So we're going to do a n minus 1 by n rectangle, 4 by 5. As you read along the rows, the numbers are going to decrease by 5, along the columns decrease by 6, and we want the whole array to be anti-symmetric. The number in the upper left-hand corner is minus the number in the lower right-hand corner. If that makes the upper left-hand corner n squared minus n minus 1. But anyways, we get this unique array like this. And now look at a Dyck path from this corner to this, not quite the upper right-hand corner, but one place to the left of that. So this path should stay above this diagonal. Look at the numbers, the positive numbers below the Dyck path. These numbers 1, 7, 2, 3, 4, 9. In increasing order. But we want to sort of compress them into a weakly decreasing sequence. So we subtract 0 from the smallest one, 1 from the next one, 2 from the next one, etc. We get this sequence. This is a partition. And this is a bijection between Dyck paths and partitions with no 5-core or 6-core. Not a little easy to prove this. That's the very interesting theorem. There's still lots of nice open problems about these cores.
Is there exact relation for other cases like n, n plus 3, n plus 2? Yes.
Yes, it's all exact. That's good. Just a special case becomes Catalan numbers, but you can generalize it to any P and Q relatively prime. If they're not relatively prime, it's infinitely many. They're still a theory. And so this shows this partition ended up with 4, 3, 1, 1, 1, 1, which is a 5, 6 code. These are the hook lengths and one of them 5 or 6. Okay. Let's see, well, time is a little short. These slides originally were for longer talks, so we'll go to algebraic interpretations. There's a lot more we can do with Catalan numbers besides count things. Maybe the simplest one, that algebraic interpretation of Catalan numbers, is as the number of two-sided ideals of the algebra of all n minus 1 by n minus 1 upper triangular matrices over some period. Pretty easy to see. One can prove that the two-sided ideal has to look like this. We take one of these rotated Dyck paths here to here. Anything above it, and any element of the field below it, 0. The set of all such matrices forms a two-sided ideal, and that is the bijection of the Dyck path. This one and go to maybe one of the deepest of all results about Catalan numbers and connected with all kinds of amazing mathematics, the theory of diagonal harmonics due to Heyman and Garcia. The main result is through Heyman. So we'll let the symmetric group act on, say, this. We have a polynomial ring A over the complex number, two sets of n variables, x1 up to xn and y1 up to yn. And x diagonally, that is, an x the same way each set of variables. So w, f of x1 is like f of xw, etc. I is the ideal generated by all invariants of positive degree, or equivalently, all polynomials with 0 constant term in this ring that are fixed on every element of the symmetry. Now, if you just had one set of n variables, it's a very classical situation. This quotient ring, you modify the idea, is a finite dimensional vector space of dimension n factorial. And Sn acts on a regular representation. But for diagonal harmonics, it's much more difficult. But the result connected with Catalan numbers is that Cn is the dimension of the subspace of this quotient ring that affords the sign representation. That is, W acting on any element F should be the sign of W plus or minus 1 times F for all time. So this is a very deep result of Feynman that involves the geometry of the Hilbert scheme.
And there's no elementary proof, right?
That is correct. No elementary. There's all kinds of, there's nice, well, this ring has a bigrading by x's and y's, and the combinatorics, that gives a refinement of Catalan numbers. I don't have time to go into that, although I do mention it in my book. And it has related to some very nice Catalan statistics. Okay, so not much time left, but let's get away from the combinatorics of Catalan numbers and look a little bit at the number theory. I said there were 66 additional problems, which are these A problems. So A61, there's a standard result. If Bn is the number of ones in the binary expansion of n, Kummer's famous theorem on the largest power of a prime dividing a binomial coefficient. The largest power of prime dividing n choose k is the number of carries when we add k and n minus k in base p. Using that theorem, we see that the largest power of 2 dividing Cn is b of n plus 1 minus 1. And this can be extended in a pretty subtle way to figuring out the congruence class of Cn modulo other powers of 2. What is Cn congruent to mod 16? Or let's look at a different combinatorial property of Catalan numbers. Let Fn be the number of integers between 1 and n that are sums of 3 squares. It's well known that this has density, limiting density, 5, 6. Approximately 5, 6, you could say 5, 6 of all positive integers are a sum of 3 squares. Was it easier or harder for a Catalan number to be a sum of 3 squares? So let Gn be the number of integers between 1 and n, such that the Catalan number is a sum of 3 squares. What is this limiting density? Do you think it's less than, equal to, or greater than 5, 6? It's 7, 8. It's actually not so hard to see that, because I don't have so much time to go into it, but it follows pretty easily from this theorem about the largest power of 2 dividing Catalan numbers and the known characterization that n is not a sum of 3 squares if and only if it's a power of 4 times a number congruent to 7 mod n. There's nice analytic properties of Catalan numbers. What is the sum of the reciprocal of the Catalan numbers? Sum of the reciprocals of the Catalan numbers. Well, if you haven't seen that, you need excellent intuition to guess this answer. Now, where did this come from? Well, it's actually done by putting x equal 1, which is this more general power series identity. the sum of x to the n over Cn. This came from, one way to do it is using this standard identity for the power series expansion, arc sine squared. You can see this denominator is very close to the Catalan number. It's not very hard to change that. And this can be proved in many ways, such as just squaring arc sine using some combinatorial identity. Yeah, we also I wanted to see if I could fool around a little bit with this and get rid of this palm here. There's something much simpler. And it turns out what you need is 4 minus 3 n over c. This sum is exactly 2. Oh, let me just mention one outlier. There's some results that just seem really strange and not related to anything else. So Euler in 1737 found this continued fraction expansion of E. I think once it gets started, these numbers just increase by 4. When you look at the convergence of this continued fraction, cut it off at some point, look at the rational numbers, and we're interested in the numerators of the convergence. So let an be the numerator of the n convergent. 3, 4 is 190. There is a result, the exponential generating function for an is the x of the ordinary generating function for Catalan. What?
Did Euler prove that?
Did Euler prove?
Oh no, he did not.
Did you prove it?
No, I did not prove that. I forgot to prove that. But how did I even run across this result? Well, anybody ever look at x, the generating function for Catalan numbers? And so I computed it. Both with and without this plus 1, and naturally, there's an obvious place where I looked up the coefficients on it. With that. And there I got this reference to this result. Okay, so that gives a very quick overview of what I know about Catalan numbers. I have come to my last slide. I will go back to the very beginning. Ming On Tu, the first person to write about Catalan numbers. Here's a page from his manuscript. And here, oops. It's hard to, it's so blurry on the screen. This is 1, 2, 5, 1, 2, 5, 42, 1, 32, etc. Each column is actually a formula written in Chinese characters. And the Catalan numbers appear exactly in this column. 1, no, you can't read it from here. 1, 2, etc. So this is where this Catalan numbers appear. This character here means this is supposed to be 5. This means less. I think this means subtract 5. Okay, so I'll stop here.
You don't have a poem with the acronym of this now?
You don't have